that I'm understandable. So what I'm going to speak about are these Goodstein principles, and I look at what I call giant Goodstein principles and illusionary giant Goodstein principles. And this is joint work with several people, a collection of possible members of the team, and yeah. Now, first, let me explain what is an illusionary giant. And actually, it's about a fairy tale by Michael Ende, which is called Jim Knopf and Luke, the engine driver. And I took a quote from Wikipedia. So Jim and Luke, they did a journey, and they arrived in a special city, Dragon City. Along the way, they make two new friends. The giant, Mr. Turtur, who is actually a Scheinriese, which in English is explained as illusionary giant. Now, what's this? Well, he only appears to be giant from afar. When approached, it turns out he is actually of normal height. Mm-hmm. And another person, which is not that important here. And in the talk, I will mainly speak about the difference between giant and illusionary giant. Now here's a photo from a painting which I made. And actually this is from a marionette theater in Augsburg. So it's a marionette of Turtur, and you see him in front of giant mountains. And so he looks very big, but in fact, when you would approach him, he would become smaller. Mm-hmm. Anyway, that's a sort of motivation. Now I come to explaining what are Goodstein principles. And I start with the classical example of standard Goodstein sequences. So I fix a number k, at least as big as 2, and that's our base. Then what I'm doing is I consider arbitrary numbers m with respect to k. So I start with the number m here, and I write this with respect to k in this way. And the point here is, so I squeeze in m in between k to the r and k to the r plus 1. And there's a unique r such that I can do this. And if I've squeezed in m in this sense, then there's a unique remainder q smaller than k to the r, and a unique number p smaller than k, such that I can write m in this way.
Andreas, I think there is a problem when you, with Zoom, reproducing your markings on this screen. So
here's the picture.
Yeah.
Anyway,
so we don't see anything anymore on your slide. Maybe.
Do you see the slide right now?
No.
I see. We see that there is a slide, but we cannot read it because everything you do with your mouse.
I see.
Now we see it again. Now we see it again.
That's very good. So let me go to the full screen again. Mm-hmm. So now you can see it as before, right?
Yes. Mm-hmm.
I see. So I will be careful in not playing with my fingers.
Not to click the mouse. Yes, indeed. Mm-hmm.
I see. Anyway, so one can write every number m in a unique way in this form. It's an exponential representation. And in doing so, I say that m has a k normal form k to the r times p plus q.
You are doing it again, Andreas.
You can't read this, or
after you touch it.
Your mouse leaves a trace which doesn't disappear.
I see again.
What
so.
I think maybe if you use the tools from Zoom, annotating tools from Zoom, that would help. But
if I click
otherwise,
this,
just
so what about this one? Can you read now?
Yes, we can.
I see. I will just use my cursor then. So you can read m is in k normal form like this, right?
Okay.
And now the next step is what I'm explaining is the base change. You can read the base change. So the idea is I take a number m, write it in k normal form, and then I replace every occurrence of k by k plus 1.
Mhm.
So I replace the base k by k plus 1, and I do it in the exponent r and in the remainder q recursively. For p, there's nothing to change because p is smaller than k and there's no base change involved. And if I have the number 0, the base change does nothing. And of course, if a number m is smaller than k, by this definition, nothing is changed at all. Now, one can show that the base change operation is strictly monotone. Moreover, if m is a term in k normal form, then after base change, the new result is also written in k plus 1 normal form. So base change preserves normal forms. Now Goodstein comes into play. So it's an English mathematician, and he studied these Goodstein sequences. Now, what are the Goodstein sequences? We start with our favorite number m, and then we start a process. We build a sequence from m. At time 0, we set m0 be equal to m. And now if we are further in time, and the number ml is not yet 0, then we form a new number. So we are considering discrete time. We form a new number ml plus 1, which results from ml by replacing base l plus 2 by l plus 3, making the number bigger. And then I subtract to 1. So normally ml plus 1 is much, much bigger than ml. And if ml is equal to 0, then ml plus 1 stays 0. Now, the surprising result by Goodstein is that for every m, there exists an L such that ml eventually is equal to 0 is true. And later, Kirby and Paris showed that this is unprovable so in first order Peano arithmetic. Now, how to prove this? So the Goodstein proof works as follows, and it's very simple. And then you take number m, you write it in k normal form, and then you move the number k to small omega. So you replace a finite number by an infinite number. So pk of m is the result after replacing k in m by omega. So it's omega to the pk of r. So we do the replacement also in the exponent. There's no base, no change of base in p, but we also replace k, occurrence of k in q, recursively we replace k by omega. And pk of 0 is 0, and pk of numbers smaller than k is the identity function. Then one can show that pk is a strictly monotone function. Moreover, pk has the following property. If I first replace in m k by k plus 1, and afterwards if I replace k plus 1 by omega, then I can do it in one step, namely I can go to m and replace k directly by omega. Moreover, if m is in k normal form, then after changing k to omega, pk of m will be in Cantor normal form. Now we start a magical calculation. We prove termination of the Goodstein sequence. So we have number m and time L. And now we study the behavior of the Goodstein sequence at time L. So we define an ordinal interpretation O of ml. What does it? It takes number ml, goes into ml, and replaces base l plus 2 by omega. Now, if ml is not yet 0, then we do a magical calculation. Namely, we study a number OM of l plus 1, which by definition is psi l plus 3 of ml plus 1. Now we plug in the definition of ml plus 1. So we get CL plus 3 of, we take ML, replace base L plus 2 by L plus 3 and subtract to 1. Now the psi L plus 3 function is strictly monotone. So this is smaller than psi L plus 3 of ML, where we replace L plus 2 by L plus 3. Now using the property which I mentioned before, this is the same as CL plus 2 of ML, and this is by definition equal to O of ML. So what does this mean? If ML is bigger than 0, then I get a strict descent in the ordinals. Now if the Goodstein sequence would never converge to 0, this process would yield an infinite descending sequence of ordinals. This proves termination. And now for proving the independence of PA, one uses two properties. One verifies that the psi k interpretation interleaves with the standard fundamental sequences. This is a technical lemma which I will not prove. And then one uses further the property that one has a certain standard form of an unprovability result for first order arithmetic. It's the so-called unprovability of the Hydra battle or something similar. Namely, the arithmetic does not prove that for every alpha less than epsilon 0, there exists an L such that stepping down along the standard fundamental sequences, starting with 0, then going over to fundamental sequence at argument 1, then going to fundamental sequence at argument 2, etc., hits at some moment L the number 0. This is a true statement because it's strictly descending sequence of ordinals which has to terminate, but the arithmetic is not able to prove this for every alpha less than epsilon 0. Anyway, now we have not yet seen giant and illusionary giant Goodstein principles. Now I will introduce those ones. For this, I switch to the standard Ackermann function. So what I'm doing here is I fix again a number k at least as big as 2, but I could also use k at least as big as 1. It would not matter here. And now define a0 kb. So it's an Ackermann function in 3 variables. And the number k is just a fixed iteration parameter. And at ground level 0, the Ackermann function is just a successor function. Now I'm defining a index a plus 1. And I assume that the function a index a has already been defined. What I'm doing is now I'm taking iterates. So I take the function a index a, I fix the k, but then I do iterates in the second argument. So I form a nesting a index a of k of a index a, and that's difficult to understand. So let me try to explain it in a different. Can you see now this screen here?
Yes.
The new screen, and actually I have here my iPad, and ai plus 1 of kb, which has been defined. I did not define it right now, but a index a plus 1 of k and 0 is what? I take a index a k.
Andreas, we don't see the text that you're writing. We see the slides still.
Yes.
You still see the slides?
Yes.
Yeah, we still see your slides.
I see. Let's see.
We see the cursor moving around, which is
inconvenient, I guess. Let's see. I go back to maybe I go back to the slides. Actually, maybe it's easier. Now you can see the slides again.
Yes.
Yeah. So I leave out my explanation, which I prepared on my iPad, because maybe it does not. I did not check it before how this works with Zoom presentation. Anyway, what I'm doing here is
only don't move your mouse.
So let's try it again. So anyway, a plus 1 of k0 is the iterate of a index a k times applied finally to 0. I hope that is somewhat clear what I understand by this.
Mm-hmm.
And now I'm considering what is a index a plus 1 of k of argument b plus 1. And for this, I use a subsidiary recursion. So I assume that a index a plus 1 kb is already defined. And I plug this into an argument of a k times iterate of capital function a index small a. So it's I use the smaller function a index a. I iterate it k times in the second argument. And then finally, I plug in the previously defined value a plus 1 kb. And that's the value of a plus 1 kb plus 1. Now for the standard Ackermann function, you would use this recursion for k equal to 1. And I use it now for general k at least as big as 2. Now it's clear that for fixed a, the function will be primitive recursive. And if I consider this as a function in a, k, b, it will be a non-primitive recursive function. Anyway, what I'm doing here now with this function is for every m bigger than 0, I will define a normal form. So there will exist unique numbers a, b, l such that m can be written in the form a k, b plus l. Now I have to define how to make a, b, and l unique. Well, a is maximal in the sense that an function a index a, k0 is less than or equal to m. So I squeeze in m between a k0 and a plus 1 k0. And then I choose b to squeeze in m between a kb and a kb plus 1.
Mm-hmm.
And then I fill up the rest with the number L. So it's a somehow very easy sandwiching procedure just in one step. And this is my normal form for M. M is in K normal form AAKB plus L. Now having fixed the normal form, I can define base change operations. The base change operation is replacing K by K plus 1. And I have 3 base change operations. The first one is as follows. Of course, if m is equal to 0, I do not change anything. But now if m has a form AAKB plus L bigger than 0, then if I do the base change in m, if I replace K by K plus 1, then I do what? In the Ackermann function, I replace the parameter K by K plus 1. And I do base changes in the indices A and in the second argument B, and I do not change the argument L. So that's a double base change in A and B, and I move the parameter K to K plus 1. The second base change, which I'm interested in, is just doing a base change in the second argument of the Ackermann function, so not in the small a, but just in the second argument b. So the rest is just the same. And the third base change, which I'm interested in, is I take my number m, write it as before in K normal form, and I only perform base changes in the index a. And of course, I change the Ackermann function index k by K plus 1. Now, given these 3 base change operations, I come to 3 Goodstein principles. While these base change operations are strictly increasing, and they move K normal forms into K plus 1 normal forms. This is sort of easy verification. Now, I have 3 types of Goodstein sequences. So for number m, I first define my Goodstein sequence with respect to the first base change operation. So that was a double base change operation. So if m0 is m, and if ml is bigger than 0, then ml plus 1 results from ml by replacing base l plus 2 by l plus 3 and I subtract to 1. And if ml is 0, it stays 0. This is exactly the same definition as before. Of course, I have now a new normal form, so this makes a difference. And the second and third principle are just defined in the same way, but here I use base change in the second argument, in the second principle. And in the third principle, I define Goodstein sequences as before, but I use base change only in the first argument of the Ackermann function. Now I have three principles. And I have three assertions for every m that exists in L, such as Goodstein sequence at the time L hits 0. I have it for double base change, for argument for base change in the second argument, and for base change in the first argument. Now the question is, do these principles, are these true statements? Any guesses? Well, it's a question into the public. So what do you think? Well, maybe nobody wants to make a guess.
Well, my guess is that they are true.
Yes, so the question is, are these all true? And yes, they are all true. Now the question is, which are giant and which are illusionary giant? So which have strong proof theoretic strengths and which are weak? That's a good question. And that's the topic of my talk. So we will answer the last question in the next slides. So I have three ordinal interpretations. So a determination proof for all these principles works as follows. So I have ordinal interpretations psi k, chi k, he k, and xi k. And for the double base change operation, the corresponding function tk of m works as follows. It has three cases. The first two are somehow easy, but in the second example, you see that I have a complicated nesting, but the base change in the index goes into the exponent, where I have to interpret the exponent recursively. If I have only base change in the second argument, then I don't need to change the indices. So the small a is not changed, it's just fixed. What we see in comparing pk with hk is that pk moves into ordinals less than epsilon 0. hk moves into smaller ordinals because what you see here is ordinal values will be smaller than omega, and in the exponents there will be ordinals less than omega plus omega. And finally, if you have only base change in the index, ck of m does basically, it's omega squared times ck of a plus omega times b plus l. So these ordinals will be smaller than omega to the omega. Now one can prove that pk is strictly monotone, and it moves normal forms, k-normal forms, into Cantor-normal forms. Moreover, the same holds true for hk and ck, and therefore, transfer induction up to epsilon 0 proves the termination of the first Goodstein principle. Transfer induction over primitive recursive arithmetic, transfer induction up to omega to the omega plus omega proves termination of the second Goodstein principle. And primitive recursive arithmetic plus transfer induction up to omega to the omega proves termination of the third Goodstein principle. Now you see three statements of different strength. Now the question is, how sharp are these bounds? So the indication is that the first one may be a giant Goodstein principle. The second would be considered as intermediate. But the third one, which looks strong in the beginning, might be very weak. And it would be then considered as an illusionary giant Goodstein principle. Now, for proving the unprovability results, one has to look into the standard fundamental sequences. They work as follows. So if alpha is a limit in Cantor normal form, omega to the alpha 1 plus omega to the alpha n, where the alpha n is a limit, then I define the fundamental sequences for alpha by continuity using fundamental sequences which are previously defined for alpha n. And if alpha is a Cantor normal form ending with omega to the alpha n plus 1, and then I use the standard fundamental sequence for omega to the alpha n plus 1, which is omega to the alpha n times x, and then I define the rest by continuity. These fundamental sequences have a certain technical property, which is called Bachmann property, which is very useful if you deal with those fundamental sequences, but this is just for information. For technical reasons, I also put fundamental sequences, define fundamental sequences if alpha is 0 or if alpha is a successor. So if alpha is 0, then the fundamental sequence does nothing, and otherwise I go to the predecessor. Now assume that m is bigger than 0, then I can show that the fundamental sequences and the Goodstein principles fit very nicely together when I use the interpretation function ck. And this is basically the same as for the standard Goodstein principle. This assertion shows by some technique that the first Goodstein principle will be independent of Peano arithmetic. But the same is true for the second order interpretation. So Ek of a Goodstein move is located in between a descent in the standard fundamental sequences. And the same is true for Ek. And this means that the estimates which I've shown before are sharp ones. Namely, PA does not prove the termination of the first Goodstein principle, primitive recursive arithmetic plus transfer and induction for an alpha where alpha is smaller than omega to the omega plus omega does not prove for every m the existence L such that ml tilde is equal to 0. And primitive recursive arithmetic alone does not prove termination of the last Goodstein principle. Voila, the first Goodstein principle is a giant one. The second one is intermediate, and the last one is what I call illusionary giant. So this is the first part of my talk. Now comes the second part. Goodstein sequences for the extended Gregorczyk hierarchy. So what I'm doing now is I consider Goodstein principles for Ackermannian functions, but where the indices are now ordinals less than epsilon 0. So recall that lambda x is the x element of the fundamental sequence for a limit lambda less than epsilon 0. At level 0, a0 kb is just the successor function as before. Now if I have an ordinal index which is a successor, a alpha plus 1 of k0 is just defined as before. It's a alpha, k times iterated applied to 0. And a alpha plus 1 of k and b plus 1 is defined as before. I first calculate a alpha plus 1 kb by subsidiary recursion on b, and I plug it into the k's iterate of a alpha. Now I have to say what I'm doing with limits, and then I'm using the fundamental sequences. So a lambda k of 0 assumes that I have defined a alpha for all alpha less than a lambda. And then I use a specific number, lambda k0, which is smaller than lambda. And I apply the a function k times. I consider the k's iterate of the a function applied to 0. I will explain in a minute what lambda k0 is. And a lambda kb plus 1 is defined similarly. I jump down from lambda to a smaller ordinal. I iterate that function k times and apply it to a lambda kb. Now, what are these indices? For limit lambda, the ordinal lambda kb is defined by nested recursion, namely lambda 0b. So the first argument gives the number of iterations. So lambda 0b is just lambda. It's the bth element of the fundamental sequence for lambda. And lambda k plus 1b is I take lambda, but now not at b, but I take lambda kb as an index for the Ackermann function. I calculate a lambda kb of kb, This produces a big number, and I plug this into the fundamental sequence. So these fundamental sequences converge a bit more quickly than the usual ones. Anyway, for every number m bigger than 0, there will exist unique ordinals alpha less than epsilon 0 and b and l smaller than omega, such that m can be written in the form a alpha k b plus l. And this is the same as before, but now I've replaced the a's by an alpha. Alpha is maximal with the property that a alpha k0 is less than or equal to m. And b is maximal such that a alpha kb is less than or equal to m. And this is a this is a normal form for m. Now I define base change. Base change goes as follows: if m is 0, I do nothing. And if m is a k normal form a alpha kb plus l, then I do the base change in m by, oh, here's a mistake. It should be, in the result, it should be k plus 1 as the first argument of the a function. But for the rest, I do base change in alpha. So a index alpha, where I do the base change in alpha, of, and then there must be k plus 1, of, and then in the second argument, I do also the base change, and then finally the L is unchanged. Now I have to explain what does it mean to do base change in alpha. So if alpha is a form, Cantor normal form omega to the beta times m plus gamma, then the base change in alpha is done as follows. I know by recursion assumption what the base change in beta is. I know by recursive assumption what the base change in gamma is. And the number m is a natural number which has a normal form. And for the number m, I have defined the base change in the previous line. So it's a complicated nested recursion, but this is a base change operation for the generalized Ackermann function. And then I do the same in the second and third case, where I do base change either only in B or in alpha. Here's the same definition and the same mistake. So in the result, it should be a alpha k plus 1 of B. I do only the base change in B. And yeah, the base change in the ordinals is defined as before. And in the third case, I do only the base change in alpha, but not in B. But it's important that I do base changes in the parameter of the Ackermann function 2. That's a k. The k is should be k plus 1. Anyway, these base changes are strictly monotone and move k normal forms to k plus 1 normal forms. This property is difficult to prove, but I will not go into details. Now I define Goodstein sequences with respect to those principles. And the definition of the Goodstein principles is no surprise. I just copy and paste the old definitions. So at time 0, m0 is m. And if ml is bigger than 0, then ml plus 1 is, I take ml, replace base l plus 2 by l plus 3, and I subtract a 1. And if ml hits 0, is 0, then ml plus 1 stays 0. And I do the same for the other principles. So for base change in the second argument, I define the corresponding Goodstein sequences. And for base changes in alpha only, I define corresponding Goodstein principles. Now you can ask, what about the statements for every m there exists in L, such as the Goodstein sequence at time L hits 0? Are these statements true? What do you think? Any guesses?
Of course, they are true.
Yes, it's true. Well, otherwise that would not make sense at all. Anyway, but now the next question is, which are giant and which are illusionary giant? Any guesses? That's more difficult to answer, and I will answer this right now. So, but now I have to go a bit into complicated ordinal notation systems. And I will sketch a bit how to do this, but if you don't understand what's going on here, just have to accept for 3 or 4 minutes that I'm speaking about these large ordinal functions, but later I will come back to less complicated ones. So I use the collapsing function of Buchholz, which is used for the ordinal analysis of theory ID1, which is basically ACA naught plus light phase binom 1 comprehension. So I define this function. So omega is the first uncountable ordinal, and C alpha is the least set C of ordinals, such that 2 ordinals 0 and omega are elements of C. This set C is closed under +1, under the successor function. And if I have numbers above capital omega, they are closed under forming omega exponentiation and sums. Moreover, if beta is element in C, but smaller than alpha, then C beta is in C. And C alpha is defined simultaneously with Psi alpha. Psi alpha is the least ordinal psi, which is no longer in C alpha. Then one can show easily by canonical argument that psi alpha is countable. Psi alpha is a limit number. Psi alpha plus 1 is psi alpha plus omega, and psi is a weakly monotone. We write beta is a normal form psi alpha if beta is a form psi alpha, and moreover alpha is in C alpha. Now what's the point with normal forms? As I said, the psi function is weakly monotone, but if I have 2 psi values, beta is normal form psi alpha and delta is a normal form psi gamma. If I have 2 normal forms and alpha is strictly smaller than gamma, then I can conclude that beta is less than delta. So in general, the psi function is weakly monotone, but on normal forms, it's strictly monotone. And of course, if you want to prove termination using ordinal functions, you have to use strictly increasing functions. Now, I define the ordinal interpretations for the 3 principles. So I use again psi, chi, and xi, and psi is for the double base change principle. And if alpha is 0, it's just a successor function. And if, can you still see the slides?
Not very well. So,
so I just use the cursor, so maybe I should.
Yes.
Okay. Now they are better?
Yes.
Yeah, anyway, I should be careful with the cursor. But the point here is that if I have an M of the form A alpha K B, then I'm using the psi function. And the psi function uses values of psi K of alpha and 1 plus psi K of B. And for this, I have to explain. So I define psi K of M, but I have not yet defined what is psi K of alpha. Psi K of alpha is defined as follows by recursion. If alpha is smaller than epsilon 0 and alpha is the form omega to the beta times M plus gamma, then psi K of alpha moves this countable ordinal usually into an uncountable ordinal of the form capital omega to psi K of beta times psi K of M. Psi K of M is defined by the previous recursion plus psi K of gamma. Now this is a bit a magical definition, and the point is one can prove if M is in K normal form, then psi K of M has this Buchholz normal form. So that's a big surprise, but it's going to happen. If M is of normal form A alpha K B plus L, and I just want to model base change in the second argument, I can use much smaller ordinals. Namely, I don't have to go into the uncountable. I can just use ordinals less than epsilon 0. And if I do base change only in alpha, here's a suggestion to go along with ordinals also smaller than epsilon 0 when I define ck of alpha when alpha is less than epsilon 0 in the following form. So these are the 3 ordinal interpretation functions. Now, eta 0 is the so-called Howard-Bachmann ordinal, and the first definition using the psi-k function yields termination of the double base change Goodstein principle. It's primitive recursive arithmetic plus this very big ordinal, plus the transfer induction on this very big ordinal proves for every m there exists an L such that ML hits 0. Then the second one, base change in the second argument only, can be proved terminating in with using transfer induction up to epsilon 0. And there is a third one is base change in alpha only. And we have seen there will be an ordinal such that for every m there exists an L such that ML hits 0. So the first might be a giant one. The second is definitely illusionary giant, because we prove termination. We use transfer induction up to epsilon 0 to prove termination of a Goodstein principle, which is defined using ordinals less than epsilon 0. So it's not much going upstairs. So it's really of low complexity. And what about the third principle? What do you believe? Is it illusionary giant or a giant one?
Well, if the analogy with the first set of principles that you had before, then it probably should be also illusionary, right?
Yes, and that is how I set up the story. But of course, there's some bad surprise, and actually I was cheating. Namely, the point is the function ck, which I was suggesting, is not monotone. So you cannot use this to prove termination. This means ck does not yield a termination proof in epsilon 0. Actually, the story is that I tried to prove termination in epsilon 0 induction, but at some moment I found a mistake, and therefore I was forced to redefine my interpretation ck. So ck, I put it again to be 0 if the argument is 0. And if m is in normal form a alpha k b plus L, then ck of m in the critical case is defined using the psi function, the Buchholz psi function applied to psi k of alpha, where for an ordinal less than epsilon 0, I really move the alpha into the uncountable world. Ck of alpha is in general an uncountable ordinal. And this is good because this will be a correct definition. So all these functions psi k, he k, and psi k are monotone. Moreover, they move k normal forms to counter-normal forms, and actually they move it into normal forms when needed into this psi normal form, the Buchholz normal form. So this is very nice. So actually one can show with transient induction up to the Howard ordinal that for every m there exists an L, ML hits 0. So for the third Goodstein principle, one can prove termination. But now the question is this a sharp estimate, or maybe it was overkill and I could somehow simplify it? Now, what would you expect? So I've shown termination of the last Goodstein principle. So I'm using only base changes in ordinals alpha. Is this sharp, or could it be simplified? And the suggestion was maybe it can be simplified, but it cannot, and that's a surprise. So we again work with Buchholz style fundamental sequences. And then the result is that in the first example, the ordinal interpretation fits nicely into this system of standard fundamental sequences. There's a sort of nice nesting property. The same is true for he k, and the same is also true for ck. And this actually shows the following result, namely ID1 does not prove termination of the first Goodstein principle. PA does not prove termination of the second Goodstein principle. And ID1 does not prove termination of the third Goodstein principle. And this is somehow surprising because it really looks somehow much weaker than the first one, but actually is not. And so that was even surprising to me. So this is now the result. And now, finally, I want to come to part 3 of the talk. Namely, you can ask the question, what is gained by all of this? Of course, you can imagine that you have many different Goodstein principles and you can play around. But what is the genuine insight? And what I want to show now is there's sort of general theory of notations for natural numbers. And let me give a small, short recap. So if, now I've used it again. So the recap is, if m is in k normal form, then after base change, k goes to k plus 1. And pk of m moves k to omega. And actually, this shows in some sense that epsilon 0 can be considered as a directed union of the exponential terms. So a so-called direct limit. Namely, if you take an arbitrary ordinal alpha less than epsilon 0, it will be in a range of some function pk, not for all k, but if k is large enough, and actually you have to choose k as big as the maximal natural number showing up as a coefficient in alpha, and then this alpha will be in the range of pk. Now we have the following properties, namely if m is smaller than n, then after base change this remains, and even after base change k goes to omega, this stays. And this is actually an idea which goes back to Girard and motivated by Fefermann's problem of what is the natural well ordering. We want to study Ackermannian functions, Ackermannian number theory representations in terms of such direct limits using what is called a dilator by Girard. Now, what is a dilator? So what is a dilator? Well, it's difficult to explain, but a working definition is given by denotation systems. So dilator is, well, so following Girard, dilator is a functor on the categories of ordinals which commutes with direct limits and pullbacks. But today we don't want to go into category theory, so there's a more concrete description. So dilator is just a function from ordinals to ordinals with certain properties. Namely, if you have a given argument alpha, then you consider the function value f of alpha. And then the set of ordinals beta less than f of alpha can be described by denotations. So for beta less than f of alpha, I will have a unique notation given by some term s, the parameter ordinal alpha, and I have a sequence of parameters alpha 1 to alpha n, which are smaller than alpha. That's just a requirement. So every beta has a unique denotation. Now these denotations are uniform in the following sense. So the denotation of this, the value of this denotation will be beta. This is uniform in the sense, if I shift around the parameters, I get a new denotation. So if I replace the alpha i's by alpha I prime, then I take the denotation s of alpha 1 prime up to alpha n prime, alpha prime, and I consider the value of it. It will be a denotation for an ordinal less than f of alpha prime. So I can freely move these parameters around, and then I switch between f of alpha, elements of f of alpha and f of alpha prime. Moreover, these parameters behave like indiscernibles. If beta is denoted by s in a sequence of alphas, and if delta is denoted by a term t, alpha and parameters gamma, and if I now replace the alpha i's and the gamma i's by isomorphic copies, and I replace them in the denotations, and if beta is less than delta, then this will stay after switching to the new situation. So what does this mean? So if I have the situation alpha I is less than gamma j, if and only if alpha I prime is less than gamma j prime, then beta is less than delta, if and only if the denotation where I move the alpha i's into the alpha I prime. will be smaller than d, where d of t, where the gamma i's are replaced by the gamma I prime. So the ordinal comparisons are stable under substitutions of indiscernibles. And every such dilator can be seen as a functor on this category, but I will not delve into it. But the point now is I want to study dilators on natural numbers. So I have the notion of an omega dilator. And what is this? Well, I take the previous slide, and everywhere where there's an ordinal, I just plug in a natural number. So an omega dilator is a function from natural numbers to natural numbers. It's a function such that for every b less than f of a, there's a unique denotation s of parameters, which are increasing with value equal to b, such that if I move around the a's by a primes, then I obtain a new denotation for an for a number less than f of a prime, so that if we have the same indiscernible effect, namely if I have b and d, b is denoted by a's and c is denoted by c's, and if I replace the a's by another a's and c's by order isomorphic a primes and c primes, then b is smaller than d if and only if the same holds after the replacement. Now we consider the following definition, namely another version of the functions which I've studied before. So a sort of extended Ackermann function. So f0 of n is a successor function. F alpha plus 1 of n is the n plus 1's iterate of f alpha, applied to n. And f lambda of n is defined by recursion. So first I calculate f lambda 0 of n, which is defined by induction hypothesis. And I use this number, plug it into lambda. And then I calculate f lambda of this number applied to n. Now what is the result? The result is, if I restrict this definition to finite numbers, then the functions a goes to fab and b goes to fab are omega dilators. So the Ackermann function is an omega dilator. That's the news here. Moreover, this can be generalized to ordinal indices. So if I have an alpha of the form lambda a, where a is an occurrence of a number theoretic coefficient in alpha, and the functions a goes to f lambda depending on this coefficient a applied to b, and b goes to f alpha b are omega dilators. Now this sounds maybe complicated, but actually it's not so difficult to show. So we show now, we give a proof of the statement that the function a goes to fab is an omega dilator. How can we do this? Well, assume that m is smaller than fab and assume that m is not yet 0. Then we approximate m by the following construction. We choose d to be maximal such that fad is less than or equal to m. If we hit m, then we have already our notation basically. Otherwise, we choose a0 to be maximal such that fa0 of fad is less than or equal to m. Then we consider iterates of f alpha 0. We choose I0 to be the maximal iteration index such that fa0, I0 times iterated applied to fad is less than or equal to m. And then we iterate this construction until we finally can write the number m as fan, in times iterated applied to blah, 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 to fa0, I0 times iterated applied to fad, and we hit number m. And this is a unique representation of m. Moreover, this is a unique representation of m, and we have two properties, namely the ai form a strictly descending sequence, and the upper iteration indices fulfill the following property, namely il is less than or equal to the following sequence of iterations. Now what's the point here? The point here is this is an if and only if. So if m has a normal form, then these two conditions hold. And if these two conditions hold, then m is a normal form. Now assume that for the upper iteration indices il, I have denotations. Then I write down a formal term c, namely I use my term for m which is in the third line, and I plug in variables for the a's. In the following way, namely C is f to the cn. Cn is already a denotation, and then I replace an by variable xn, and I go further and further, and then I have f to the c0 index x0 of fxd. That's a formal term where the parameters a are removed, and the number m is denoted by the expression where I have the term c and the parameters al and a. And that's a unique denotation. Now the trick is, if I replace the a's by a primes, then I want to have a unique notation for number less than fa prime b. And actually this is true. The point is that I know that I have a unique representation for m. This gives, by some sort of induction, that the IL are less than or equal to this iteration. And then by some induction hypothesis, I can assume that less than relations are preserved under moving around parameters. So if I change IL and go over to IL prime, then it's less than or equal to the following iteration. And this yields that normal forms, after replacing sequence of parameters by a new sequence of parameters, preserve normal forms. Moreover, if P is less than Q, P has a normal form in this way, Q has a normal form in the other way. And if I now replace parameters by equivalent order indiscernibles, then I want to know that after the substitution, P and Q are in the same relation with substituted values. Now, P is less than Q if the sequence of pairs given in this way is lexicographic smaller than the other sequence of pairs. And this is again an if and only if. Now assume that I have a sequence of parameters AL and BL smaller than A prime, which is order isomorphic to AL, BL, and A. Now let P prime and Q prime be the results after replacing in the unique representations of P and Q the parameters AL, BL by AL prime, BL prime. Then by corresponding induction hypothesis, the sequence of pairs shown to the left is lexicographically smaller than the sequence shown on the right, because I have assumed that these base changes, that order relations are preserved under indiscernibility. And then P prime will be smaller than Q prime. This shows the indiscernibility condition. So that's somehow very interesting. Now the question is, what do we have from this? Well, first let me remark that by similar reasoning one can show the more complex statement, namely that A goes to F lambda A of B is also a delator, but this is more difficult to show. Anyway, recently I showed this to our team in Ghent, and Johan Aguilera said, well, maybe you can more with this. And actually, my conjecture now is that we have the following principle, namely over ACA0, the following will be equivalent. ATA0, so predicative analysis, is equivalent with the statement that the omega dilator, which I just defined, namely A goes to FA0, extends to a dilator. Now, what's the trick here? I have an omega dilator by the theory of Girard. It extends uniquely to an operation moving linear orders to linear orders. And now, if one has a property that this extension preserves the well orders, then it extends to dilators. Now the principle that this omega dilator, the Ackermann function, extends to a real dilator, this should be equivalent to ATA0. And if this works out, and I believe in this, then this would give a fanatistic approach to the recent groundbreaking work by Anton Freund. Namely, in the following sense, one can show if one has a strictly increasing omega dilator F, one can define corresponding function f epsilon 0 of f, where f0 of f is the function small f. And I think I will be able to show that there's a transition. If you start with an omega dilator, then the new function is also an omega dilator. And then there's a principle for all strictly increasing omega dilators f. If f extends to the dilator, then f epsilon 0 of f extends to the dilator. This principle might be equivalent to pi-1 comprehension. And this would be a rather interesting application. And that's basically the end of my talk. So what I want to show here is Goodstein principles are not just play with specific definitions, but it leads to a theory of notations for numbers, which can be used for all different purposes. And finally, let me do some advertisement, namely we have 2 PhD fellowships available in Ghent. So if there might be some interested people, please have a look into this. There's also more, there are more possibilities in Ghent. If you're interested in coming to Ghent at some moment, there's a page related to research in Ghent. There are bigger projects available for senior people. Some of them are even equivalent to an ERC advanced grant. And that's now the end of my talk. Thank you very much. Okay, and now I'm back.
Thanks. Mm-hmm. Okay, can you perhaps say what are the groundbreaking results by Anton Freund that you referred to?
Anton Freund has a very strong result, namely he has defined a principle that every dilator has a certain Howard-Bachmann fixed point. And he has shown that this one is equivalent to pi-1 comprehension.
Mm-hmm.
And what's very nice with this approach is that there's no hand waving involved. So you can just take his paper, you can read it line by line, and there's no question mark. So the problem with papers which I had in the past, the papers by Girard, is that it's somehow difficult to figure out what's really behind them. And Anton has really brought it to the point. And this principle by Anton is a new one. So there are some principles of Girard which somehow indicate in that direction, but this is now really, in my opinion, a groundbreaking result, which is quite surprising that with these dilators, you can characterize a complicated principle like pi-1 comprehension.
Okay, yes, that's the results he talked about in Barcelona, I guess, maybe somewhere
Yes.
else.
Mm-hmm.
Mm-hmm. Okay. Okay, let's ask the audience for questions. And let's see the chat. Are there any questions in the chat? It is not, doesn't seem to be the case. Okay. Yes. Okay.
Yeah.
Sergey, you have a question, so please.
Yeah, I have a question. What about worm principles? Are there illusionary worm principles or real worm principles? And that's a question maybe to Lev too.
I would guess so, yeah.
So here we have sort of analogy with Goodstein based on, let's say, very roughly on this representing numbers via systems of notations related to Ackermann function and faster growing functions.
Yes.
So with these worm principles, we don't, at least I don't see any generalization like that would work. Which is not which doesn't mean that there are no such possibilities to generalize Hydra principle or worm principles, but I don't know such things. So that might be a good question to think about.
But Andreas sounded a little bit more optimistic about this. Maybe he sees more.
Yeah,
well, let me say it's just a belief. So I have not yet.
Intuition. Let me say intuition because believe it's too low the term.
Yeah.
Good.
Because with these things, it's a matter of naturality, how all these notions, whether it's natural to generalize it in this way or not.
Each of the constructions which mentioned, Goodstein, Hydra, and Worm, they have their own naturality. And that's why they have their own motivation. And but it's an it's an interesting approach to look at through the fairy tales of the 19th century, I guess. Illusionary giant. Good.
Anyway, interesting that in this area, presumably well trodden for decades, still some new phenomena suddenly appear. So this generalization of Goodstein looks very natural, where you plug in, instead of exponential representations, you consider other systems of functions like Ackermann or higher. Somehow people didn't notice these phenomena, especially the last one where you get up to the Bachmann-Howard and higher.
Yeah, I also thought about. I think that the key point is that you reproduce the culture as a senior academic or academic figure. You just teach your students, and you teach them deeply, and you teach them all the classics. And if you have enough young brains in the area, they will keep digging. And clearly, each of the corners of the thing is infinite. It has an infinite depth, so you can keep the new results, as natural as the old ones, will keep coming as soon as you reproduce the school, of course.
Okay, Andreas, can we see your face perhaps? Because we see.
Yeah, I'm just looking for. Yeah.
Your pictures are nice. Don't take us wrong. We love them all. Yes.
What's happening here? Yeah, so I just want to turn my camera on, but yeah, here it is. Let's see.
Oh yeah.
Now I'm back. Yeah. Now I'm
back.
Yes.
Okay. Yes.
Anyway, I still have to learn these buttons.
Yes, we're all learning. So.
Yeah. Well, what is the major issue with all these? What is the problem in defining Goodstein sequences for these Ackermannian terms is the non-unique representation. So if you have a number m, you have infinitely many ways to write m in terms of the Ackermann function. Therefore, the base change operation is not well defined. And the trick in all of this is to single out the unique representation. And for this, you need a specific choice. And you have to figure out what is the most canonical choice to write m in terms of an Ackermann function. And I think this is what the people haven't seen before. So that's the new aspect.
Exactly. And they also perhaps wouldn't have guessed that suddenly the principles might become stronger than the original Goodstein. So a priori, it's not obvious that changing these representations, you would get something higher up.
Yes. And there's something more. The real magic is if I move Ackermannian terms into the higher ordinals. So if I have these Ackermannian functions with levels less than epsilon 0, and I move them into the higher ordinals, then I use the Buchholz function psi. And there the complete magic is if I have a k-normal form for natural number, and I move it into the uncountable, this countable stuff, that I get values in Buchholz normal form. And that's something which you, in some sense, would not expect. So that's I have no explanation for this. And so in the beginning, I was using a different collapsing function, which was not depending on normal forms. But there were disadvantages because then you got other problems to work with. And
yeah, something with the norms probably, right? So that's your older approach was using this.
With the norms, and well, somehow is just the beginning to something, but I think these normal forms is something really which is a new aspect. And I believe that the naturalness of all notation systems has to do with the naturalness of notations for finite numbers. So this back and forth between finite numbers and uncountable numbers reflects the naturality of the notations. Well, that's my personal opinion.
Okay, okay, no, that sounds good. Of course, this interest towards delators, so re-emergence of delators in the study of proof theories is also quite a positive development. Yes, Sergey, please.
Lev and Andreas, unfortunately, I have to go because there is something else I have to attend. So, Andreas, very nice to see you in good spirits and very fine math. I really enjoyed it. Thank you.
Yeah, thank you for
thank you for being with us. Yes, bye bye. Okay, anyone has more questions, or shall we slowly close our seminar today? Okay, people seem to be silent, but there are signs of applause. And many thanks for quite a curious talk by one of our, by Daniel Ragozin. So, okay, thank you very much, Andreas. It was really very.
Also my thanks. It was a pleasure to be in, and yeah, I'm sorry for these problems with the screen, but this
no, not a big deal. So this was not a big deal. The talk was dense. Maybe therefore some people are sort of slow on asking questions. But anyway, next week we will have a talk by David Belanger. So everyone is welcome, and I hope to send the announcement as soon as I get the abstract.
All right.
Okay. Thank you very much, and yeah, till next week.
Yeah, thank you very much, and
bye bye.
see you.